Okay, I'm going to combine square roots, logs, and exponents in one video here. I guess it's the highlights of what we've done the first week, and we'll add to each of these calculations as we go along. But this is the kind of the bare essentials, what you need to get started in order to have future conversations and deepen your understanding of functions, which is a fancy name for calculations. So I've started with some truisms that are on the board, and when we get to each one, we'll use it. So the parent function. This is what a square root function looks like. Right? The square root of 0 is 0, and then the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, and it looks like it starts somewhere, then goes up slowly. Slower and slower and slower, increasing because it takes more area to produce 1 unit of change. And hopefully you can freeze this and look at it a little bit. And you can probably see a pattern. The first change is 1 between integers, now friendly integers. I'm talking about user-friendly numbers. The next gap is 3 units. The next gap is 5. You probably can see 1, 3, 5. Yeah, 7 plus 9 is 16, and the square root of 16 is friendly. In other words, you don't need a calculator. But that's the parent function. So how do we write? Name that tune. If I throw some different numbers your way, let's say I give you 5 gets us to 7. And how about we do, I don't know, and 11 gets us 10. Okay, hopefully I picked out something that's nice. Well, again, you have to think about what a square root is. A square root is a side of a square. Simple enough, but I don't know how many people really make that connection, and I want you to make that connection. Got the sun in my eyes over here. I'll go with it. I can put this down, get a little bit more of the screen, and hopefully, wow, I think I'm going to pull the blinds down, so bear with me. I think that's the only one now I gotta do this one too. Be there a moment. Video's no good, you can't see it. The other rooms were being used. Am I there? No. There, I think that'll suffice. All right, so I was talking about square roots being a length. All right, we're not gonna, the length gets smaller and smaller and smaller, right? We can keep doing that until we get 0, and that's what kicks off the parent function. So I want the 5 to act like a 0. This should not look surprising at this stage that I start with that statement. And the radical symbol acts like a parentheses, but it's an operation. And so I put a 5 in, the square root of 0 is 0. I want a 5 to get me a 7. I write a 7. I'll put y equals. And then I put 11 minus 5. Well, 11 minus 5 is really that length. But it's not a square. A length isn't a square root. Unless, well, I said the wrong thing here. 11 minus 5 really gets us 6. Yes? Didn't mean to say it, but rushing around a little bit, I did. So square roots, this is an area statement. Right? So 6 units means that length is the square root of 6 by definition. And so I put 11 in, and that gets me the square root of 6 plus 7. And I'm trying to get to 10. So that numerical change is not friendly at all. So we get rid of it. And what is the number we want to get from 7 to 10? It's 3. And so that's what that equation would be. I'll do one more because I kind of, didn't do that cleanly. So I'll just make some new numbers. How about minus 3 gets us 8. And let's go with 12 gets us 9. Make it nice and simple. So negative 3 means I say x plus 3 in order to get the square root of 0, which kicks this off. And then if I put, and I want to get an 8, so I add 8. Hopefully the numbers are starting to speak for themselves. how do I get from 8 to 9? I know I want to add 1 to 8. So whatever comes here, I got to cancel. Got to get it out of the problem. And what do I get if I put a 12 in? A lot of you might still say 15, but no, 15 is the area. It's the square root of 15 that is generated. And if you put that into a calculator, you're going to get that graph. All right, so that's going to be asked on Tuesday. What else is going to be asked on Tuesday? Well, let's start with something that is already written. Can see up there? Yeah. 2 times 3 is 6. The square root of 4 times the square root of 9 is the square root of 36. I hope you can see that the square root of 4 is 2, the square root of 9 is 3, and the square root of 36 is 6. What I learned from that is if I start with one number and I multiply the square root of another, then I can put the product inside one radical symbol. Now, why is that helpful? Because there are a lot of square roots that are nice. Now, what are the nice square roots? You see this? Yeah, I think so. You know, it's the inverse of squaring. Squaring should get you the familiar 0.149 units of area. Well, over here, area is what we're taking the square root of. The square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. Nice. Okay, so where does that lead us? That leads us to be able to do a problem like the square root of 75. Because I know that the square root of 75 is the square root of 25 times the square root of 3, which is equal to 5 root 3. And ancient mathematicians, friends of mine, you know, from hundreds of years ago, well, they had a real good sense of what the square root of 3 is, probably better than I'm going to write. I'm just, you know, approximating to 2 decimals, 1.73, and I put that on a memorization sheet and ask you to memorize it. If you're like any other class, you haven't yet. But if you're going to study trigonometry, you're going to need those 2 values, or you're not going to understand any of the amounts that you're studying. All right, so square root of 2, 1.41, square root of 3, 1.73. Going to work with them extensively. Half a semester will work with numbers like this. So I hope you take the time to memorize those 2. All right, and then I can look at this and go, well, that's a 5. That's a 5 with a carry of 1. Okay, and that's a 5 carry of 1, 6.55. That doesn't, so I did something wrong there. I'm tired, it's Friday afternoon. So 5, 15, 35, 36, carry a 3, 5, and 3, 8. That's more like it. So that's pretty close to the square root of 75, 8.65. I put it in Google, find out how much of an error there is. But it's a field. It's a field that I didn't have until I wrote it 5 root 3. And so it was helpful. All right, so what else is there? Well, there's problems like what's the square root of 7 times the square root of 14? How would we do something like that? Well, I know now from over here, let's make sure that you can see this. We'll start with something we know. Square root of 9 is 3. And therefore, the square root of 9 is 3. And 3 times 3 is 9. Well, that means the square root of 9 times the square root of 9 is 9. It's true. Well, if that's a 3, then the square root of 3 times the square root of 3 is 3. And I know a square root times a square root generally gives you a square root. And it does. Square root of 3 times the square root of 3, but it gives you the square root of 9, which is 3. And we want to skip right over to that. All right, so how does that help us with a problem like this? Well, I know the square root of 14 is the square root of 7 times the square root of 2, and I'm multiplying it by the square root of 7, so that's going to get me 7 root 2. And we haven't practiced these problems as much as some others, so I would anticipate that it might take a little longer to learn than the scrimmage on Tuesday. But we'll keep doing it like every other problem, and hopefully understanding will accrue. All right, so that's another type of problem that I'm going to ask you. And I'll give you one more like it because you haven't done as many. So what's the square root of 5 times the square root of 10? Hopefully you can do it in your head pretty soon. Well, that's the square root of 5 times the square root of 5 times the square root of 2. There's the picture of the square root of 5 times the square root of 5, which has got to give us 5. So I'm going to rename that more easily. And I get 5 root 2, which is approximately 5 times 1.41. It gave me one more chance to tell you what the approximate decimal equivalency is. of the square root of 2. Again, that'll be helpful at some point. What other questions? I kind of put them over there. Yeah, I lost a lot of sleep looking at, this distance here. The distance, if this is 3 and this is 5, what's that distance? I lost a lot of sleep with that. Kidding, of course. And what I'm hoping is that you look at that and you say, well, that means this is 25, right? That's the easiest way to do the Pythagorean theorem is pictorially. That's 9. And so what does this one have to be? 34. And then what is this distance by definition? Square root of 34. A little less than 6, right? Square root of 36 is 6. I don't think there's any perfect squares in there. No numbers like 4, 9, 16, 25. So that's it. So this is the square root of 34, and therefore I put it with the square roots. I could have put it with the quadratics. I didn't think of it. All right, so what's another one? Another distance. Another distance is the distance between 2 points. Let's do 3, 5, and let's go to 7, 9. All right, well, again, you might be better off putting the x's in the table. So from 3 to 7, I believe, is a unit of 4. I'll put it on top. And from 5 to 9 is another unit of 4. Oh, wow. So distance, right? I did the horizontal change, the vertical change. Pythagoras again, there's 16. There's 16. And 16 and 16 is 32. So that's the square root of 32. And I hope that you write the square root of 32 as, maybe written as, the square root of 16 times the square root of 2. And there's your 4 root 2. And you can get a feel for it if you multiply 4 times 1.41. All right. Forgive me if I'm a little slow on my feet at the moment. Been at this all day. And I just mowed the lawn. Get a little tired because I'm an old man. What else do I want you to know at this stage? I think that's it for square roots. Just those 4 problems, or 5. I think I did 4 or 5. They're going to get a little harder as we go along. We're going to build our repertoire, but we got to get off the ground here. Okay, so what's the next thing? Did I miss anything up there? I don't think so. Okay, so that's enough for square roots right now. And considering that we've only had 5 days of school, and one of them was a little bit of introduction, I think we're moving along nicely. It's one of the harder moments in a term, getting this process underway. And then we'll get a chance to see how you're coming along. And if somebody's really struggling, might change the way we approach the studies that we're putting in front of you. Okay, I said square roots, exponents. Yeah, where do we start day 1 with exponents? Understanding the rules. Oh, that's not what I wanted. I wanted a 2 and a 3. Right? So those are the 3 things you're asked to do to this number. And we looked at that for a couple of days. The order doesn't matter. So what do we have? We have a minus sign. What is that rule? Flip. Flip the number. Right now you got 8 over 1. Okay, we could make it 1 over 8, and we use that operation. What's squaring? I shouldn't have to explain that. That's doing 8 times 8. That gets us 64. Okay, that's doable. And what is the 3? The 3 is cube rooting. Okay, I like to go small than big. So I'm going to do the cube root of 8, which is 2. And that leaves me with 2 to the minus 2. I'm going to do 4. So 2 squared is 4. I'm going to do that operation. That still leaves me minus 1, right? Minus 1 times 2. I did that operation. I still need that one. And I know that's 4 over 1. So my answer is 1 over 4. So right now, I know that I know that 8 to the minus 2/3 gets me 4. And we're going to be practicing exponents to amounts. And we're going to be doing that in a moment. Okay, so given the base, changing exponents to changing amounts. Fine. There's another way to write this relationship. And it's amount to exponent. How do you go from amounts to exponents? And that, my friends, is an absolutely new operation that you have just started to see. Maybe some of you know what to write. How do I go from the 4 back to the minus 2/3? Well, I do it by writing first. I want that exponent on top of an 8. That gets me a 4. And let's figure out how to get this. Let's pretend we don't know. That's my amount. I'm sorry, that's my exponent. I said the wrong thing. This is the amount generated by that exponent. And we're going to find that now. How do we do it? Oh, this was 1/4, wasn't it? I just botched that, right? Because I forgot to write the flip. So how the heck do I do that? How do I get that exponent for this problem? So forgive that faux pas. Won't be the last one I make in this video if I continue the way I'm going. Well, the first thing you do is you have to understand the command. And we talked about that on day 1. Log is the exponent. You put on top of an 8 to get a 1/4. Well, rules of exponents, this was on one of your worksheets, a to the 4, b to the 4. Well, you can't say anything because rules of exponents require the same base. So if I had a to the 4 times a to the 4, well, that's actually a to the 8. And Tiffany made a nice worksheet for us. You go look at it. That's probably on there somewhere. This rule, right? What's m squared times m to the 5th, m to the 7th, and I think she showed why. So get that, pack it out. And if you didn't get the pack it out, it means you don't have it, which means you probably didn't pick it up and ask for it. All right, so what's the same base? How can I express the number 8 and 4 exponentially? Well, 8 is 2 to the 3. And I can raise that to the x power. And 1/4 is 1 over 2 squared. Running out of room here. But this is equal to 2 to the 3x. And this is equal to 2 to the minus 2. All right, the minus sign is telling you that the squaring of 2 is taking place in the denominator. So I'll come over here because I don't want to bend down. Well, now that we have the same base, then the exponential activity has to be the same. And 3x has to equal -2. Therefore, x is equal to -2/3. Oh, yeah. That is what that x value was. Okay. So in this case, this is where our x's are going to be, and this is where our y's are going to be. And I'll do another one of those and see if you can maybe try it. But we got Monday still to work on these. Maybe I'll make a worksheet for Monday, let you work through it. Because if you're watching the video, which is what we did in class today, on quadratics, I hope, and this one as well. So let's look at log base, let's see, 25 to get 125. And what's the exponent? Let's get this exponent goes on top of 25 to get 125. How are we going to do it? Write an equation. Bring the exponent over. Set it to 125. Okay. I don't see the same base right now. This is 125 to the 1. Can't do anything, but I could sure rename 25 as 5 squared and then use my rules of exponents to get 5 to the 3. And if I do look at that, then 2x equals 3 and x equals 3/2. So I'm going to put that on top of 25 and look at it. And I hope you're starting to understand what operation that is. It's a square root. All right, so the square root of 25 could have been written as 25 to the 1/2. That's helpful to know. So what is the square root of 25? 5. What is 5 cubed? 125. We now know that the exponent that works is that. Okay. 25 to the 1 is 25. 25 to the 2 is 4 quarters makes $1. All right, so that's $6.25. So 625. Does it make sense that 25 to the 3/2, which is 1.5, in between these, that might give me a number between these? Yeah, hopefully you're making that connection too. All right, and what else do we have? Yeah, we got exponential functions, graphing exponential functions. I'll just give you a growth function. So a b to the x, if b is bigger than 1, we have growth. On top of usually a constant. Could be plus or minus, but usually there's a constant. If you don't see a constant, it's plus 0. All right, so I'm going to ask you to graph and then name that too. So let's do graphs first. Let's graph y equals, how about I go 10 plus 7, 2 to the x minus 1930 over 17. Now, 10. All of this growth is on top of 10. I've got a 7 and a 2. What you're going to find out is if you pick the right numbers, you're going to go up 7 and you're going to go up 14, because what's 14 divided by 7? That 2. That ratio of change, any two numbers, any two differentials can make the base of an exponential function. The only difference is if I pick the difference over here, then I'm not looking at a doubling over a certain elapsed time. I'm looking at something bigger than doubling over a longer period of time. But it could be the same numbers generated. So there's what I'm basically trying to say is there's an infinite number of ways of writing this, but I'm writing this based on what I see. Okay, I'm seeing 17 units, 10 plus 7, and I'm also seeing 10 plus 14, 24 units, provided I can pick the right numbers. And what are the right numbers? Whatever you have, you want b to the 0 and b to the 1. So I want x minus 1930 over 17 to equal 0, because we've looked at that in class. B to the 0 is 1. Okay, b to the 0 is 1. And if I can make that 2 to the 0, it becomes the number 1, and my first jump is 7. And b to the 1 is b. We have knowledge of that, easy knowledge of that. All right, we could do b to the 2, b to the 3. We could, but these are the two easiest to see with practice. And so if I make this thing the number 1, I get 2 times 7, which is a jump of 14 on top of 10. All right, so what numbers am I picking to make this 0? 1930. 1930 minus 1930 is 0. 0 divided by 17 is 0. 2 to the 0 is 1. 1 times 7 is 7. Plus 10, 17. And that happened with 1930. And this number, I don't know if that was the same number I had. I can't remember. Let's make it 19. Let's make it 37. It may be a new problem now. I can't remember what I had there. Old age. So what does this do? Well, it affects my x table, just like a linear function does. Right? So I want to look at 1967. Because I'm trying to get 1. Right? And if I want to make that the number 1, well, then I've got to get x alone. I'm going to multiply 1 by 37, and then I'm going to add 1930. And that has moved these and given me the x value that I want, 1967. So if I put 1967 in here, let's do it. And I'll give you another one like this. X minus 1930 over 37. Okay, I'll put 67 in here, 1967. 1967 minus 1930 is 37. 37 divided by 37 is 1. I don't need a calculator to do 2 to the 1. It's 2. And there's 14 plus 10, 24. And that was in the year 1967. I think we've done logs, which is the inverse of this. I'm not going to do that right now because I want to practice the exponentials. And I probably will not ask you to write I might ask you to graph the inverse, give you a picture, graph the inverse. What's the inverse of y equals 10? X equals 10. What's the inverse of 1930, 17? 17, 1930. And if you got an eagle eye, you might see that that's 7 units of change. And then 24, 1967. I'm just going to do this one time. And how do I get from 10 to 24? 14 to, used to be vertical ratio of 7. Sorry, this was 7. Right? It used to be a vertical ratio. Now it's horizontal, but we're doing a logarithm here. And the way you'd handle that, which is the inverse of this. So if we call this f of x, then this will be the inverse function. Right? Which is another way of saying y equals. So I'll do it with y equals. The first y I see is 1930. The next y is 1967, a jump of 37. It's a logarithm. I got an x equals 10. So I got to pick numbers bigger than 10 because all my y values are bigger than 10. Now my x values are bigger than 10. And I can show that by x minus 10. And therefore, this only works for numbers bigger than 10. And I hope you can see that. This graph looks like that. And every x value here is bigger than 10. Maybe somebody in the class will get this right, take the time to learn. So then I start using my next x, which is 17, and 17 minus 10 is 7. And then I use my next x, which is 24, and 24 minus 10 is 14 divided by 7, which is 2. And so that's the inverse. And I can show you the inverse by plugging 1967, I'm sorry, by plugging 24, right? This was an in on this graph. So in the inverse, that's the in. Let's put 24 in there. 24 minus 10, 14. 14 divided by 7 is a 2. Do you know what log base 2 of 2 is? Do you know what it's asking yet? What do you put on top of a 2? I'll make it an x value. What do I put there to get that? That's a 1. What's 1 times 37? 37 plus 1930. There's your 1967. Okay, so I probably will. Do I have expectations that you own that yet? Absolutely not. But somebody might. Somebody might surprise me, take the time to look at it and play that again. All right, so let's get another one here. Let's do Newton's law of cooling, which is an actual law of physics. I brought my coffee in, right? And when I poured it 3 minutes ago, so that'll be -3. 3 minutes ago, I poured my coffee, it was 140 degrees, right? And I know something about Newton's law of cooling, but I didn't. Let's say 5 minutes from now, it's 100 degrees. I really don't know if that's the length of time for that. But the numbers are going to work out here. So you try to get that function. You know, what's y? We've only seen it 2 minutes ago. What do we start with? The most important temperature on the board is the room temperature because the coffee is cooling to the room temperature. So I'm going to put a 60 down. I won't put the degree symbols. And I want to get to 140 because I'm reading from this perspective to the right. I could have gone backwards, but confusion more. So how do you get to 140? That's 80. Now what is that 80? It's this differential. We just talked about those differentials in the last problem. What's this differential? 60 to 140. So what's happening here? The differentials are being cut in half at the same elapsed time. What is that elapsed time? Oh, from -3 to 5, every 8 minutes. The differential is being cut in half. And that is Newton's law of cooling. He gave us this formula. Okay, so sometimes the numbers aren't pretty. So the second differential comes from not adding 80, but adding 40. That's the hard part of this. The easier part is -3 and 5. So there's your x plus 3 over 8. Right? That's what we're doing with the linear function. Making a 0, making a 1. When I put 5 in, I get 1. When I put -3 in, I get 0. And that is that equation. Woo! All right. So is that it? Is that all I wanted to say? Well, that's all I'm gonna say. There may be something else on those worksheets, and I'll look at those tomorrow and Sunday. And maybe there's something there that I'll ask as well. It can only help you. The more things I ask, the more checks you get. So the more questions I ask benefits you. All right, I've had enough. Been a long day, so I will try to find my cursor. I can't even see it. There it is. Bye-bye. Have a good weekend. I'll upload this to your Canvas.